Welcome back.
Hello.
I missed you.
Oh.
Did you? I'm not gonna ask. I've noticed that it takes a little bit of warm up, right? Once you come back from spring break, it really. So we're gonna start easy, and then we'll just ramp up the difficulty. Okay. Right. So first question.
Fun day.
Okay. And then getting a little bit harder now.
Opposite down.
Okay. Really pushing the boundaries of mental computation the day after spring break.
I wish it was
You wish it was me? Well, maybe it is. Maybe physics is the thing that pushes against chemistry.
Does that mean chemistry is the dark arts?
Uh-huh.
Okay, I'm down for that.
And then finally, the impossible question,
Oh,
which
God. What?
I'm only seeing realization in about 2 or 3 people's eyes.
You.
This is from a movie. No? No? Okay.
What's the movie?
Monty Python Search for the Holy Grail.
Oh.
Go watch it when you are in an altered state. It'll make sense. All right. It is a weird movie, but very fun. What were we doing? We were doing physics. That's where we started anyway. Maybe where we should start. Let's see. I actually had to check YouTube this morning to see where I had left off. Right? And I think we've done that problem. And then I wanted to do another example. And again, we'll use this as a little bit of a recall and warm up and things like that. In terms of like class business and stuff, I did post the topics. Somebody called me out for not indicating which one was the conceptual question, so I updated the topics. It's the history of light question is the multiple choice one. But that's a little bit of a trick, right? Because they're kind of all conceptual, right? Like if you can't nail the concept of thin film, you're not gonna get it right? So that caveat is always in place. But let's see, and then we'll finish chapter 27 today. Tomorrow homework is due, is that right?
Yes.
Right, and we will do the review for the exam, and we'll be having the exam on Thursday. I did contemplate the idea of sort of pushing everything back, and it just wasn't working. I know I can sometimes I can start a new material before we're testing on the old material, but in the case of modern physics, it's such a complete 180 degrees from what we've experienced so far, I didn't want to do that. Because it would just mess you up. So we're gonna plow ahead. You're gonna do just fine. I believe in you. You've got this, right? We'll spend today and tomorrow just making sure all of our ducks are in a row. All right. So when it came to doing thin film problems, there was a picture that we had to have down on the page before we could even really figure out anything else that's going on. You identify thin film problems by the word film in it somewhere, right? Okay? And not like photographic film, but just this thin layer that's sitting on top of something else, right? And so I just usually draw, right, that film is this, there's an interface with the air, whatever's above it, and then what's below. So we've got oil film on a water puddle. So what's on the bottom?
Water.
That's the water, okay? And then here's the oil. They don't tell us what's on top, so what do we assume? It's just air, okay? So we know that this one's 1.25, we know air is 1, and they don't tell us what water is, but we can go look it up, it's 1.33. Okay, now before we even figure out what they want, we've got to figure out the physics of what's going on in this situation. So, first bounce, right? Light comes in, bounces off the surface, what's it going to do? It's going to reflect, but there's something that happens to that light. There's a switch in the phase or the orientation of the wave. We're going from a low index to a high index.
Oh, it's 100.
It's a 180 degree flip, that's the rule, right? Okay, so we go from 1 to 1.25, that's a 180 degree flip from the original. And then we have the ray that comes down and bounces off the bottom. And what condition do we have there? High to low, low to high. This is a lower to a higher, 1.25 to 1.33. So again, we have a 180 flip. So if we leave the relationship alone, notice I said the words leave the relationship between the two waves alone, don't change anything, but I wrote down that equation. That's because that's what that equation says to do with the physical situation we have, right? Whatever the situation is, leave it. That's what that equation says. If we leave it alone, are these two bounces, are they constructively or destructively interfering with each other? One's 180, the other's 180. What are they going to do when they get together? Be the same or be different? They're the same. Even though they both flipped 180 from the original, both of them together are 180. So how do you get constructive? There are all possibilities for constructive. You could have 0 and 0, right? Okay? But you could also have 180 and 180. How do you tell if it's destructive? What's going to be true? They're going to be different from each other, right? One's going to be 0, one's going to be 180, either or, right? Okay? So the fact that both of these are 180 means that they are in phase with each other. And so this equation is the constructive equation. Remember, this is something with thin films you got to do every single time. You're deriving the application of the equations. The equations say the same thing all the time. This equation says don't change that relationship. And so if we don't change it, that means for this particular problem, this is constructive. The other equation, m plus a half lambda, means you add 180 to the second bounce. So 180 plus 180, that's 360, which is also like 0. Remember, anytime you go around the circle, you get back to where you begin, right? So the fact that these are now different, right? One's 180, one's 360 or 0. This means that this equation is going to be what? The destructive equation, which I already labeled right there. Okay, we've done the setup, right? And that's like the same, you go through that same process for every problem. And then comes the part where you got to figure out what they're asking you about, right? Okay, so they tell us that green light is absent. What are they not telling us but trying to tell us? What are words like absent or missing or interfered? What kind of interference is that? That's destructive, right? So that wavelength, 521, is absent. We've got to be using our destructive equation. And I think that's like a separate problem from the setup. You got the setup, right? And this issue with figuring out what the equations, how they apply to the situation, right? But then you have this separate thing where you've got to figure out what they're asking you about, right? So clue into words like absent, missing, reduced, destroyed. They'll use some language. And of course, right, during the exam, you can come up and ask me, right? Because I'm not so much trying to test your reading ability, right, as I am, can you do the physics of the problem, right? So if you're unclear, just come up and ask me, and if it's not wholly pertinent to the problem, like it's not what the question's asking, I'll be like, yeah, that's destructive. Because I tend to read some of these words and don't realize that other people don't understand them. All right, what are they asking me to solve for? Thickness, right? They're asking for thickness here. So I'm gonna solve for thickness, that's gonna be m plus a half all over 2 times the index of refraction. What index am I gonna put in there? Which index do I always put in there? Because there's 3 indices of refraction, aren't there? So which one is it? I just didn't hear you. The one in the middle, the 1.25. It's always the index of the film, right? You need the other indexes to know what the bounce is gonna be, but then the one that goes in this equation is the film. They've asked for the minimum thickness, so what's M right here? Remember? It's a good spring break, wasn't it? It's a counting number. It just goes 0, 1, 2, 3. It's an integer, right? It's like a multiple. And so I can put basically any number I want in here as long as it's an integer number. But how would I get this thickness to be as small as possible? What m do I pick? 0 in this case. If we've got m lambda, you can't pick 0. Well, I mean, you can, 0 thickness film, right? But if we have plus a half, we can't use 0. So we pick 0 for m. For the minimum, right? They're looking for a minimum thickness. So this would be 0 plus a half over the wavelength times 2, and then I put in the 1.25. So that's basically lambda over 4 times 1.25. Said it wrong, wrote it right. Where's my answer? The green one. Are we at 521? Yes. I got 104 nanometers. You just put 521 nanometers in there. The 4 has no units, the index of refraction has no units. So like whatever units the wavelength is in, you can kind of keep it, because they're probably going to ask you about that anyway. 104 nanometers is my answer. Do any of you remember any of them? Yeah, it's like, there was something about this I remember, right? Okay. So between those 2 examples, the one I gave last time and this time, I think I've covered sort of all the different possibilities. I believe the 2 problems had it so that in the one case, the 2nt equals m lambda was the destructive case, right? And so on and so forth. So just realize, and again, the caution here, the thing I warn you against, because it's what you want to do, it's what you want to put down in your notes, that like 2nt equals m lambda is always constructive. It's not, right? It changes depending on the situation, and you do have to do the work to figure out whether it's destructive or undestructive. And you'll know by doing the physics of this picture over here.
Just for
Or 50-50 chance you can guess.
clarification, if it was destructive, the example, then 2nt equals m lambda is gonna be destructive, and the other one is constructive. So like,
Only if that second bounce,
Yeah, it was-
like it went air, oil, air.
right, if it was 180 and 0,
Yeah, yeah,
then it
yeah.
would, okay,
Mhm.
that makes sense.
Okay. What does this have to do with anything? Does anybody know what these are? No? These are the bumps, greatly enlarged on the surface of a DVD. Now I know DVDs are like cassettes now, right? Or like what's physical media anymore, right? But you still are somewhat familiar with, right, sticking a movie into a player to get it and not just stream it. But these are the ways that a DVD encodes information. So why are we talking about that now? How does your DVD player, your Blu-ray player read information off of that disc? Well, but yeah, there's bumps on the disc, but how do the bumps get read?
Lasers.
Lasers! Right? There's a laser in there, okay? And it's reading it. the disc actually has all of the bumps on the bottom. So if you're looking at your disc and you got the label on top, okay, there's no data there, right? It reads from the bottom upwards, right? So a laser beam comes in and strikes the surface, bounces off, and comes back. But there's actually two beams that get pushed out by the read head, okay? And if you look here, this beam bounces off the top of one of those features. They're called pits, even though something upside down their heels. Anyway, okay? Do you see how this first one bounces off the top of the pit, but this one bounces off the bottom? The feature height, the pit height, okay, is tuned so that those two waves destructively interfere with each other when it comes across an edge. If this beam were sitting over the top of the pit, the two beams would bounce off, they'd bounce at exactly the same distance, and they would be in phase with each other. But when they hit the edge of a feature, they'll go out of phase with each other. And what will the read lens over here see when these are out of phase? When they're in phase, what do we call that? Constructive or destructive? That's constructive, but when they go out of phase, that's... So what is the thing that's looking at the laser going to see? Nothing. It's going to go from seeing laser light to not seeing laser light. And how do all computers want to store or read information? In binary. On or off, right? And so now we have an optical way to read on and off. As that disc spins in there, the laser stays put. It sees a series of constructive and destructive pulses, and every time it sees light, it goes 1, and every time it sees no light, it goes 0, and it reads that string of 1s and 0s, and you get whatever movie it is you want. I mean, streaming's really no different. We just take the physical disc out and send the string of 1s and 0s to, compressed over the internet. But this phenomenon of thin film interference, this isn't technically a thin film. We're just reflecting 2 rays, but we're taking advantage. In fact, that feature height is always 1/4 the wavelength of light that you are using to read the disc. So why 1/4? Well, if it's 1/4 the distance, by the time the beam comes up and comes back again, it's half of a wavelength off, which makes it destructive. So this is probably before your time. CD-ROMs and music CDs could only store about 760 megabytes of information. A DVD can store about 4.2, 4.7, depending on the DVD, gigabytes of information. And a Blu-ray can store up to 34 gigabytes of information. The physical size of all of those discs is exactly the same. In fact, most players can read all of those formats. Like if you have a Blu-ray player, it can read all the older formats. It has actually different lasers in it for it. But the physical size of the disc isn't changing. And the way you store more information is by making the feature size smaller and smaller and smaller so you can stick more of these pits on the surface. Why do they call Blu-rays Blu-rays? They're using blue lasers, okay? And so a blue laser, let's talk about wavelength. Remember Roy G. Biv? Where are the long wavelengths? Big fat wavelengths. Over here, okay? Lambda big. Over here, lambda small, right? So the shorter the wavelength, the smaller the wavelength you can use to read the information, the denser these features can be. Remember, it goes as quarter of the wavelength for the height, and you can squish them together and all that kind of stuff. And so that's why we can store more information on Blu-ray and then use interference to read it back. All right. At this point, I decided to throw out the subject of interferometry. You can thank me later. It's actually really, really cool. We'll probably get back to it when we get into modern physics. I'll swing back around to it. But we're going to save time. We're going to jump straight into diffraction. In fact, I'm pretty sure I managed to not assign an interferometry problem on the homework. It's probably gonna get me in trouble. Did anybody remember anything mentioning interferometry on the homework? Good, okay. I had to go in and take one out. I'm pretty sure that was it. Okay, so this is the last kind of big topic for this entire unit. So what have we done so far? We've done reflection, we've done refraction, so mirrors and then lenses, Snell's law, lenses, that sort of stuff. We've done interference, and now we're doing diffraction. Those are the four wave phenomenon. Reflection and refraction, those can be done by particles. Okay? The way you know that you're dealing with waves is if they interfere and or diffract. So interference, right, is when waves get together and do something. Diffraction is the bending of a wave around an obstacle or through an opening. Let me show you a video. And maybe, well, it probably won't make sense, it's physics, but it'll start us.
We'll use this ripple tank, which projects an image of waves on the surface of water, to show diffraction
So these
through
are
a
waves
single
coming
slit.
down.
If we put
Plain
a
waves.
single slit in front of the waves emerging from the slit are no longer plane waves.
See how they spread out?
Waves are now diffracted strongly
That's
to the side.
diffraction.
If we
The
decrease
bending
the
of a wave
wavelength,
through an
the
opening.
amount of refraction is reduced. This split-screen view shows the diffraction at two different wavelengths.
You can see wavelength affects the amount of
Increasing
diffraction you
width of the
have,
slit also decreases the diffraction
as
of the
well
wave.
as how big the opening is, right? That wave is trying
This
to pass.
split-screen view shows the diffraction with two different slit widths.
And we'll get into the relationship between these widths and wavelengths here in a minute. But I wanted you to see what diffraction was. Now, diffraction patterns in optics are going to look hauntingly familiar. I mean, what does that look like already? Where have we seen this kind of pattern before? You can't remember, Mr. Bear, asking me questions, it's not fair.
We've seen it.
We've seen it. This looks like an interference pattern, doesn't it?
Yeah.
Okay, the Young's double slit interference thing where it's got the bright, like the central max, and then, right? But yes, it looks like an interference pattern, but this is in fact a diffraction pattern.
We'll shine the beam from this laser through a slit whose width can be varied by turning a screw. Here is the laser spot on the screen when the slit is open wider than the beam.
Really big slit.
We'll close the slit down part way. The laser spot now appears to spread out slightly. As we continue to narrow the slit, a pattern of bright and dark spots appears on the screen.
So obviously narrowing this down causes the diffraction to be more stronger.
When the slit is almost closed, the pattern spreads out so far it nearly disappears. As the slit is opened again, the spot narrows, and the pattern of bright and dark spots reappears.
But did you see how that central maximum was changing its width? So we don't really get that in interference. In interference, you get that central maximum, and then you get the dark and bright alternating going off, okay? In diffraction, the width of that central maximum is controlled by how big, in this case, the slit that the light was trying to get through. You can get diffraction around things.
Light passing a thin wire is diffracted. We'll use a thin wire and a laser to show the pattern of bright and dark spots caused by the diffraction. Here is the setup of laser, wire, and screen.
So really tiny wire.
This is the laser spot on the screen with no wire in the beam. This is the diffraction pattern obtained on the screen when the wire is inserted.
So we got the same pattern even though it wasn't trying to pass through something and bending out, it was trying to pass around the wire, okay? And as it passes around the wire, it also changes its direction. And then, you've already seen it, but I'll show it to you again. Poisson spot. Remember Poisson? Right?
Although light has properties similar to those of waves, The wavelength of light is so small that we seldom notice the wave-like nature of light. This pinpoint light source will allow us to demonstrate that wave-like nature. If we put the light source behind a small sphere and look at the light coming past the sphere, we see a pattern around the edges caused by interference between different waves of light.
That's actually a
Notice
diffraction
the
pattern
bright
instead
spot
of
in the
interference.
center of the
He's wrong.
sphere, where you would normally expect
And
no
that
light
dot
at
right
all.
there is also from diffraction. Okay? It's not totally wrong. So the interference fringes around an object are initially caused by diffraction, the bending of waves around objects. It's just when those waves bend, they start to interfere with each other. That's the pattern.
The diffraction causes the interference.
Yes, diffraction is the bending of a wave around something or through an opening, okay? Think of it as around the edges of an opening or that kind of stuff. I'm gonna do some more examples. But when you have like a light source, in this case you're using a laser, and you get a shadow, right, where the light can't be. But if you look really closely, like if you really zoom in on what's going around near that edge, diffraction is happening. It's bending these waves. And as the waves get bent, and it depends kind of how far away they are from the edge, they'll start to overlap and interfere with each other. And here is a really, really good picture of Poisson's spot. Right, again, remember Poisson was that guy that was fighting against Thomas Young. Thomas Young, just to review for your conceptual question, right, okay? We had Thomas Young who thought light was a wave, right? You had Newton who thought light was a particle, right? And then a good piece of experimental evidence for light being a particle were black and white photographs. Right, because the light came in these discrete chunks. And then who came along and gave like all of the mathematical formalism and showed that light was indeed a wave and is the reason we've been talking about this for the last 3 weeks? Yeah, my favorite Scottish guy, James Clerk Maxwell, right? So you want to associate Young and Maxwell with waves, Newton with particles, Newton in black and white photography with particles, right? Okay. But Poisson was the one that didn't believe in the wave-like nature, right? And he's the one that came up with the correct description for why this spot even exists. It's because light bends around that little sphere and it joins up in the middle, causing this diffraction spot and the diffraction pattern around the edge. Okay, so what's kind of the same and what's different here, and how do we navigate what's going on in diffraction? In diffraction, the setup is, for now, a single slit, okay? One opening that the light's trying to come towards, and then it gets spread out as it goes, okay? And instead of trying to kind of keep track of all the individual waves and things that are going on in here, we concern ourselves really with slit width, distance to the screen, and then the features that are going on the screen. And I've got to make sure that I use the same symbols as your book, because I was taught different symbols. Okay, so this is going to look familiar, and I apologize, I'm sorry, we just have run out of letters, okay, to keep track of stuff. But notice how there's an angle in there, right? Sine of that angle, okay, is equal to m lambda over w, where now w is the slit width. I don't particularly like w, I usually use d because everybody else uses d. So you might see this on the internet, in other sources and things like that. They will write d sine theta equals m lambda. Your book is trying to help you here in this instance. They're actually doing a fairly decent job of it. But the diffraction equation is usually written like this in almost every other physics textbook. Okay? The problem is that this is exactly the same equation for Young's double slit interference. Okay? And so your book is trying to underline, okay? So basically, instead of D, they use W. And instead of putting the W over there, they put it over here, just to make it look different, right? So that it's easier for your brain to sort of, but it's I don't wanna say it's coincidence. I'm not deriving any of this for you, we don't have time and it's boring. I did show you like how to think through the double slit with the path length difference equals a condition. When you do all of that stuff for diffraction, it's no surprise you come up with the same sort of relationships where the bright things, okay? Okay. The problem is that this equation references, okay? Make sure your book does it that way. I didn't write that down. Yes, okay. That's the equation for the dark spaces. So when you stick in m equals 0 into this, that's the central bright fringe, like before. But now m equals 1 is this dark spot right here. M equals 2 will be the next dark spot. And in diffraction, we really don't bother counting the brights, okay? We're more interested in where the pattern is dark for reasons that you're going to see here in a second. So that's a little bit of the mathematical formalism of diffraction. I don't want to linger too long on it because the applications of diffraction are more interesting. Think of this as like the Young's double slit thing where I'm like, this is kind of what's going on, but now let's go do something real with it, okay? Because there's actually more application to this than you might realize. I do want to mention this, do an example of using the equation I just showed you, and then we'll get into actual real life applications. So one of the things about a diffraction pattern that is distinct from an interference pattern, interference patterns tend to like kind of keep their brightness. They do fall off, but they're like that central bright maximum and then the ones next to it and keep going out, they stay fairly bright. It can be difficult with your eyes to really see where they're starting to dip. That is not true for a diffraction pattern. One of the ways you can tell the difference between a diffraction pattern and an interference pattern is number one, the central bright one tends to be like really big and then the subsequent ones tend to be very narrow. Whereas in interference, they're all more or less even. But look at how the brightness falls off. I don't know if you can even see it. There's a really faint red line right here on either side. And there's even one right here, but it's really, really hard to pick out, right? This picture on top is an intensity chart. So the higher the curve here is, the brighter it is. You see how right in the center right here, we've got basically all of the brightness? And then as it comes off, it like really falls off. We're gonna get back to this when we start talking about resolution, because this is really, really important for our ability of our eyes to be able to resolve things. But let's do an example of just working our way around a diffraction phenomenon, and then we'll get into diffraction gratings and applying this stuff. Okay, what do I know? Notice, the operative equation, okay? This problem, sometimes they're being really cagey about whether it's interference or diffraction, right? It's all in the same chapter and they just want to make it harder for some reason, right? They don't come straight out and tell you it's a diffraction problem. But the way you tell it's a diffraction problem is that there is a single slit, right? If this were an interference problem, they would have told us like there's two narrow slits a distance apart from each other. That would be interference. But here we have a single slit, and I'm actually going to draw this a little bit wider, just so we can, right? This distance right here, that's W. W. And they give me that that's 0.210 millimeters, right? And then on the screen over here, I've got this like pattern, right? I've got that central maximum, right? And then I've got the next bright spot and a bright spot up here. Those are the, funnily enough, those are the bright ones. But where it's absent, this is m equals 1, this one's m equals 2, okay? They're telling me that this distance right here, that central bright, is 8.5 millimeters. And then they want me to find out how far away the screen is. Our relationship was this, right? So what do I know, what do I don't know? Do we know the wavelength? Yeah, they gave that to me, right? Do we know W?
Yes.
Yeah, they gave that to me. M, we're gonna play around with, remember it's a counting number. We can do 1, 2, 3, we'll sort that out in a second. The problem is this angle, they didn't give me any angle, did they? So we're gonna use the same trick that we applied with Young's double slit, that small angle approximation, where we can write sine theta as y over L. Don't panic over whether you understand that or not. I'm never gonna ask you about the small angle approximation. Just realize that we can take advantage of it, and where y, again, is this distance from the center, the m equals 0, up to wherever it is you're talking about something going on. We know that it's 8.5 millimeters for that entire central bright thing. So if we go to the first dark, because it's the central bright and then there's a dark and a dark on either side, right? We know the total, let's say the total distance is 10, just to make the math easy, right? What would y be? Again, y is measured from the center. If this whole distance is 10, it would be 5. We're effectively cutting right in half. We're going from the m equals 1 to the m equals -1 down here, right? And this y is going to be 8.5 millimeters divided by 2, which is 4.25 millimeters. So from the center of that bright to the first dark fringe is going to be 4.25 millimeters. We're being asked to solve for L, which is going to be y times w over m lambda, and we want to really make sure that all of our units are correct. Notice I've got millimeters and there's nanometers in here, right? So there's all kinds of units all over the place. So make sure that you convert them all to meters if you want to be safe. The slit width is 0.210 times 10 to the minus 3. And then for m, we're going to put in 1, again, because we used that central bright fringe, which is bookended by 1 and -1. And then we only used half of it. So m equals 1. And then 530 times 10 to the minus 9 meters. And if we do all that, we should get our answer in meters. Where's my note? Nope, not there. Where'd it go? I swear, sometimes pages fall out. In this case, it's very definitely good. Anybody get it before me? It's 3. You beat me to it, just shout it out. Come on, you guys must have beaten me by now. I got 1.68. Yeah? Okay, so just realize that you can if they ask you for the angle, just solve for the angle, right? Inverse sine of whatever, right? But length, distance to screen, where you are on the screen is tied up in that angle, and a small angle approximation can save you. But I show you that just as an application of that equation. More interestingly, and what I'm focusing on, okay, is applications of diffraction. So let's do that now, okay? And to do that, I need everybody. 1, 2, 3, 4. Need everybody to take a pair of glasses. Pair of glasses for people. Your special physics glasses. Okay, so you get your glasses, you go ahead and put them on. Ooh. Like seriously, who needs drugs? We've got physics. Okay, so if you look up at the lights, you'll see a bunch of pretty rainbows, right? Okay, I'm gonna turn the lights off. Mostly off. Ooh. So dark. This is what it's like when every time I come to class in my mind. All right. Okay, now look at that. Does everybody see that?
Yes.
Okay. If you take your glasses off, you'll just see a light bulb. Go ahead and see it now, right? You just see the color of the light bulb, right? Okay. So what the diffraction grating is doing is it's splitting the light up that's coming off of this light bulb into that rainbow that you see. Okay. But the thing I want you to really kind of concentrate on, or at least realize what's going on here, do you see multiple versions of the same pattern happening? Like you should see the bright light, and then around it you should see a collection of rainbows, right? And then outside that you should see another collection of rainbows. And maybe even a third one, depending on how far away you are from the light, okay? So what you are seeing are repetitions of the diffraction pattern. And that's going to be important. Each one of those replications of the pattern is called an order. So you have the 0th order, which is the main light coming through, okay? And then you have m equals 1, the first order pattern. The glasses you are wearing are actually stupid because the diffraction axis is happening in 2 dimensions. This is not normal. The diffraction gratings we use in science are single axis only, meaning you'll just see a rainbow on either side, okay? But these are made to be, oh, look how trippy it is, right? Okay, so they do it in all directions. Really 2 dimensions, and so you get some off on the edges. But you'll have the 0th, you'll have that first pattern, which is m equals 1, and then the pattern repeats, that would be m equals 2, and if it repeated again, 3, 4. Depending on the diffraction grating, you can see multiple orders of the same exact pattern repeating itself. Now, we're going to come back to diffraction gratings when we get to modern physics and we start talking about atoms. Because diffraction grating is going to help us figure out the light that comes off atoms and give us the fingerprint of atoms. But I wanted you to be able to see all those different orders in these, what are quite literally groovy glasses. No? No?
No.
Oh, I forgot to warn you, public service announcement, it is April Fool's today, okay? While I am a believer in fun things, I think April Fool's is stupid. And it became much more stupid with the invention of the internet. So do not believe anything you read today, okay? I will never try to fool you like, say, oh, the test is tomorrow. So dumb. Anyway, but I do like practical jokes when they are not malicious or designed to hurt people, right? Anyway, the diffraction grating. You got to see, okay, what's going on here. And, this is what's going on. This is going on. So the glasses you were wearing quite literally have there's not grooves, there's actually allowed transmission. Anyway, we won't get into the physics of that. But there's lots of little gouges, okay? Very fine line gouges in there. It's very hard to see with your eyes, okay? And together, right, all of those different little gouges are producing these patterns and multiples of these patterns, right? You got the zeroth, which is the main light source that you were looking at, and then you have these replications of the pattern that were taking place. Each individual little pattern, right, is being produced, right? So I was making sunlight over there, okay, right? So you can see the full rainbow. But as the light hits that diffraction grating, okay, passes through it, it will spread it out not just into rainbows, right, the full spectrum of what the light is doing, but also these different orders. And they kind of get spread out, they get kind of elongated the further away that you get. We're going to keep track, okay, of what order we're on, as well as the angle that those orders are taking place from the center. So I hope it comes as no surprise to you, okay? Again, let me make sure I get the same, yeah. The equation for diffraction gratings is sine theta equals m lambda over d. It actually turns out that this is the universe's version of an April Fool's joke. Double slit interference, single slit diffraction, and diffraction gratings are all d sine theta equals m lambda. They just are. For the double slit, d sine theta equals m lambda are your brights, and d sine theta equals m plus a half are your darks. For a single slit diffraction, d sine theta equals m lambda is for your darks, dark patches. And for diffraction gratings, d sine theta equals m lambda, m counts the order that you are on, d is a measurement of how far apart two adjacent slits are, and in this case the angle is no longer small. We are not allowed to use the small angle approximation when it comes to a diffraction grating. So no small angle approximation, okay? We are stuck here because the angles are usually like 20, 30, 40, 50, 60 degrees. And I know some of you who have gone through chemistry are vaguely familiar with what I'm talking about right now because you probably looked through a spectrometer at some point and saw how the thing that you were looking at, the gas tube or whatever, right? You had these different wavelengths and you had to measure an angle that those wavelengths were at to be able to figure out what the wavelength was. That's one place where diffraction gratings are used. I'm going to show you a bunch of other things, okay? So that's what's going on with the diffraction grating. Just realize no small angle approximation, and m counts a complete pattern. And if it's the third complete pattern over from the center, you're at m equals 3. This is aforementioned DVD disc. Okay, do you see the bright rainbow in there? Those pits are etched in a spiral pattern going out on the disc. And that means that you get these features that are offset from each other. And so what you end up with is a reflection diffraction grating. So instead of light being transmitted through it, it reflects off, gets diffracted, and you start seeing the different, you see white light shining on it, you get to see the rainbow. If it's not white light, it'll be whatever the spectrum is. But this is like the first order, okay? You're seeing central zero, first order diffraction gratings in the bottom of those discs. I came in on my infant son one day. I was supposed to be watching him apparently. I'd walked out literally for 5 seconds, I promise. It was not that long. And he was sitting on the floor. He just barely kind of learned his colors, and he was still in a diaper, that kind of thing, right? He was sitting on the floor, And you know how babies do it, they're cross-legged and one leg's like sticking straight up and all that kind of stuff. And he was sitting on his diaper and he was rolling kind of back and forth on the diaper, and I thought, oh my gosh, this is not good. But he was rolling back and forth saying his colors. She was like, blue, red, yellow, green, red, right, back and forth. Oh my gosh, my son's autistic. Right, like I couldn't see, like I had walked in and I was watching him do this and I couldn't really see kind of beyond him. As I walked in further, I noticed that he had taken all of the DVDs off the shelf and opened up all the cases, right, and had spread them out on the ground. And he was sitting so that the sunlight was coming in, hitting the discs, and he was seeing the rainbows. And as he moved, as he rotated, right, he was changing the angle that he was looking at, right? He was seeing different colors being, you know, maximized in that reflection. I was like, it's my son. Right? When you're doing this with the intent to actually measure something and use it, you'll usually have a setup where you have this grading and then the ability to measure the angle that you are seeing. And so they'll use, it's actually a telescope. It's actually an optical thing that lets you kind of zoom in on what's going on, but it will also tell you what angle you are looking at for a particular thing. And when you look through the eyepiece, or the computer looks through the eyepiece, this is what you'll see. This is that bright central maximum. This is the actual object that you're looking at. In this case, like a gas tube, maybe it's argon or something, helium that's been electrified, okay? And then you'll come over and you'll see your first order pattern. But again, it's a mirror, right? Both of these are the first order pattern. And they're complete spectra of this thing that's in the center. And then the pattern repeats itself. And that will be the m equals 2. And what you can do with the device is you can say, okay, this is 0 degrees, and then you can measure, like, what's the angle separation from the center right here to this first pattern, or what's the angle separation to the second pattern, so and so forth. So let's just do a calculation using the diffraction gradient. And I'm sorry, I really am sorry. This chapter can be confusing. So thin films is hard. There's a lot of steps in thin films, but at least it's different from the diffraction gradient, okay? Double slit, single slit double slit interference, single slit diffraction, and diffraction gratings all mathematically kind of look identical. And so the differences between them are very slight. You're welcome that I didn't put all 3 of those on the exam, right? I made sure to concentrate on thin film interference, and then we're gonna do resolution, an application of diffraction. But before I can teach you about resolution, I've gotta help you understand what's going on with diffraction here. Okay, so wavelength, we got that, good. Okay, we know it's a diffraction grating because the problem tells us, right? So we know that the equation we're going to be using is m lambda, sine theta equals m lambda over d. Okay? When they say 5th order maximum, what's m? It's 5. It's 5th order, so m is going to be equal to 5. The angle that they get that at is 32 degrees. Okay? Now, they're asking us for the density of rulings on the grating. What? What does that mean? The density of rulings is measured in lines per length. I know you're used to thinking of densities as like volume mass density, but densities can actually be linear densities, surface densities, volume densities, whatever. But the density of rulings of a grating are the number of lines, number of openings, okay, per length. Usually lines per centimeter. That's typically what a grating will be rated at. So if it ever asks you for the density of rulings or the slit spacing or anything like that, sometimes they give you the ruling of the grading, that's what they'll call it, okay? And they'll say it's 560 lines, so let's say for example, they say it's 560 lines per centimeter. To get D, you invert that. The inversion of 560 lines per centimeter, okay? 1 over 560 lines per centimeter. What would happen to the centimeters in this case? Since it's in the denominator. Denominator of a denominator, what happens? It flips into the numerator, doesn't it? And then you get centimeters per line. So if you want to know the distance between two of those openings on a diffraction grating, and all you know is the density of lines, invert your number and you've got it. The only problem is, take note